Boundary is of two type: fixed boundary or moving boundary. We also call it as flexible boundary. When we say fixed boundary, again come to our example, cylinder piston example. Now you tell me which type of boundary it is. As there will be combustion here in combustion chamber, these gases will push this piston down. So this piston will move. As this piston is part of boundary, see, this is boundary. This gases, which is our system, is surrounded by this boundary, which is real boundary here, physical boundary. Okay, this is our boundary. This whole piston is our boundary. So this piston will move from this position to this position, suppose. Okay, suppose this is TDC position, top dead center, you know this, and this is BDC position, bottom dead center position. So this piston will move from TDC to BDC. Why? Because there is combustion, and because of combustion, internal energy has increased of this system or of these gases. These gases will push this piston down. So displacement will be there, and we say we have got work done. Okay, this pressure into volume displacement, P delta V, is our work done. So here you can see this piston is moving, means our boundary is moving. So this type of boundary is nothing but moving boundary. And what is fixed boundary? Suppose we fix this. Okay, we fix this piston with the help of one profile here. Now this piston cannot move above TDC. It cannot move above this point. It means the piston is now fixed. This portion of boundary is already fixed. It cannot move. Okay, it is housing. It cannot move. So if we add heat to this system, or if this system is combustible gas and combustion happens, okay, the combustion is the source of heat here, and if that combustion happens, what happens? Internal energy will increase, means pressure will increase here. So pressure was P1, it will increase up to P2. Temperature was T1, it will increase up to T2. And unlike moving boundary, this piston will not move. Okay, as this piston will not move before combustion, how much is the volume? This much is the volume, let's say V1. And after combustion, if we check it after 5 minutes, after some time, how much volume we are getting? V2. And here, what is our analysis? V1 is equal to V2. Why V1 is equal to V2? Because boundary is not moving, right? It is fixed boundary. Now you tell me, in this case, are we getting any work done? No, we are not getting any work done, because delta V is 0 here. To get work done, what we required? We required delta V positive value. Okay, so what is formula? P delta V. So when this pressure is applied on the piston, who will apply this pressure? This pressure is applied by system, these combustible gases. Okay, we know hydrocarbon, suppose CH4 is there in this combustion chamber, which is our system. CH4 is our system. This CH4 will get react with oxygen. Okay, so CH4 plus O2 is our system here. When these combustible gases will burn, when there will be reaction in between hydrocarbon and oxygen, what we are getting? We are getting CO2 plus we are getting water vapors. Okay, after complete combustion we are getting CO2 and H2O plus we are getting heat. So heat possessed by these combustible gases, okay, these gases will possess this heat, means it will not like here at this portion we are having all the heat in the system, here CO2, here H2O. Okay, this will not happen. Here this H2O plus H2O, this H2O plus CO2 in this combustion chamber will have this heat, and these combustible gases will push this piston down and there will be displacement. But in case of fixed boundary, what happen? The piston will not move, the pressure will increase, gases pressure will increase, its temperature will increase. Okay, if this boundary is intact, perfectly insulated. Heat will not transfer to surrounding. Okay, heat will not transfer to surrounding. Heat will get intact. Internal energy will remain constant. Okay, only pressure will increase here, but delta V will be 0. So what work done we are getting? P delta V. If suppose our work done, so before combustion the position was 1, after combustion the position was 2. So during process 1 2, or during burning process, the work done what we are getting, that will be P delta V. Delta V is equal to 0. So how much work done we are getting? We are getting 0 work done here. So this type of boundary is not useful for us. If we want to obtain some work done from heat, we should not have a fixed boundary, otherwise there will be loss of work. Okay, how we are getting heat? When we use petrol, we use some combustible gases like methane, CNG gas. When we burn all these gases, hydrogen is there. When we burn all these gases, we are getting heat, and these gases are not free, friends. We have to spend some money for these gases. So if we cannot utilize what heat we are getting from these gases, then there is loss of work done and there is loss of money. That's why we have to use it properly. That is our aim in thermodynamics. We are always interested in efficiency. What is efficiency? Output upon input. So what is output here? What work done we are getting from the system. What is system? These gases. From what done we are getting from this system, and how much heat we have generated from the system after combustion of the system. How much heat we have generated? That is nothing but heat supplied. So W upon Q. So W should be larger as possible to get maximum efficiency of any system. So that is about fixed and moving boundary. We can classify this boundary as a real boundary and imaginary boundary. That is another classification. Imaginary boundary. What is real boundary? Now let's understand this with one example. Suppose we are having one centrifugal pump. This is our centrifugal pump. Okay, what is mechanism of the centrifugal pump? There is one impeller inside. This impeller is attached to one motor, electric motor. So when this impeller will run, what happen? There will be negative pressure here. As there will be negative pressure and there is positive pressure or atmospheric pressure in this side. Okay, this is delivery side, this is suction side. Suction side means this pipe is deep into well. Okay, there is one well, water well. There is water here, and we have to pull this water. Okay, and we have to supply it to, suppose, farms. Okay, so this impeller will rotate. There will be negative pressure and there is positive pressure here, means pressure will be high here and pressure is less here. So water will flow from high pressure to low pressure, and this water will get pulled like this. Okay, this water will get pulled and it is supplied to farms. This way it works. Now what is real boundary here? See, this impeller has casing here. Can you see that? This impeller has casing. So this is nothing but real boundary. Physical boundary is nothing but real boundary. We can see this with our eyes. Okay, so this real boundary is nothing but this housing. And what is imaginary boundary? Sometimes what happen? See, what is our system? This water is our system. We are pulling this water from this well. This well also has water. So when we analyze pressure of, suppose, water, pressure of water. Now which pressure you will measure, or where you will measure pressure? At this point you will measure pressure, at the final stage you will measure pressure, at the initial stage, or before this initial stage. Here also there is water. So at what point you will measure pressure, or at what point you will measure temperature, volume? Okay, so what you will do, you will imagine one boundary here for thermodynamic analysis. So your analysis will be easier in that case. See, can you see this dotted boundary? So in this example, I have drawn this dotted boundary, which is imaginary boundary. So when I will measure pressure, when I will measure temperature, when I will measure volume, internal energy, enthalpy of system, I will measure properties of system which is lies inside this boundary only, this dotted boundary only. So that is our imaginary boundary. But actually my boundary or real boundary is this much, my real boundary. Okay, this housing is nothing but my real boundary. So this way we can classify real boundary and imaginary boundary. There is one another classification, that is diathermic and adiabatic boundary. Okay, diathermic and adiabatic boundary. Now what are these boundaries are? See, when we say diathermic boundary, suppose I am having one container. Okay, in this container there is water. As this water will get heated, suppose this is burner, I am using burner to heat this water. There is suppose CH4 gas, and that gas will burn here and heat will release with this reaction, and this water will get heated. Now see, when this water will get heated, the heat will transfer from this system, this water is our system, heat will transfer from this system to surrounding. Surrounding is what? This atmosphere is nothing but our surrounding. So heat will transfer from system to surrounding, and also some matter will transfer. This water will get vaporized and this matter will get transferred to surrounding. So there is Q and mass will transfer to surrounding. Now you can see I have kept one lid here. Now when there will be heat transferred to this water, or when there will be heat added to this water, see, the heat will transfer from this system to surrounding. Now you can see the heat has transferred through these walls or through this boundary, right? What is diathermic boundary? Diathermic means we also call it as conductive. Okay, suppose we are having one system, again let's say cylinder piston. This is combustion chamber, this is piston. When there will be combustion inside, what happen? Heat will transfer through this walls or through this boundary. This is real boundary. This piston will move down, but it will get heated and heat will transfer through this piston also. So there is transfer of heat. This is made up of metal, the boundary is made up of metal, so there is always some loss, okay, loss of heat through this boundary. So this type of boundary is diathermic boundary. Heat can easily transfer from system to surrounding. See, what is system here? The gas is system here, and surrounding is, suppose atmosphere is our surrounding. So heat will transfer from system to surrounding through this boundary. Easy transfer will be there. So this type of boundary is nothing but diathermic boundary. Another boundary is adiabatic. Now what I am doing? I am going to insulate these walls. I am going to insulate these walls with some perfectly insulated material. So what happened? Heat will not transfer from this system. This is our system. The gas is there. Any gas. Air will be there. CH4 will be there. Any gas will be there. So from this system, heat cannot transfer to surrounding. Heat transfer will be zero. We can obtain work done, but we cannot transfer heat. So that type of boundary is nothing but adiabatic. Here also this piston is insulated and we cannot transfer heat. This is not fixed, but it is insulated. This is gas inside and heat will not transfer. So this type of boundary is adiabatic boundaries. So what we learn about boundary? Boundaries are of two types, that is fixed boundary, or it can be moving boundary. It can be real boundary or it can be imaginary boundary. It can be diathermic boundary or it can be adiabatic boundary. In adiabatic, what happened? Q is equal to 0. Okay, actually we have to write Q12 because it is path function. We have to learn this concept path function later. Now one important thing about system and surrounding is, suppose this is our system and this system has some heat or it has some internal energy. This internal energy will get converted into work done. To do so, we are using one mechanism, it is called heat engine. So here this heat which is possessed by the system, possessed by the gas in the system, will convert into work done by using the heat engine, which is nothing but a mechanism. Now the interesting thing is, we cannot convert all this heat into work done. Means if we say efficiency is 100%, that is not possible. Okay, that is not possible. That is violation of law of thermodynamics. We have to study first law, second law in thermodynamics. So in that law we will study the 100% efficiency is not possible. Now why not it is possible? Because always we use surrounding with system. We are not using system alone in thermodynamics. We always use system with surrounding. Okay, otherwise the heat transfer is not possible or work transfer is not possible. We cannot use a single heat reservoir or we cannot use a system alone to get work done from that system. Okay, with the help of this heat engine we are obtaining work done, from the system we are obtaining work done, but only these things are not possible. There is always surrounding that works with system. So suppose if we transfer heat Q1 from the system, this heat engine will obtain work done from this Q1 and there is always some Q2 loss. So here we can write, we have supplied Q1, we have got work done, 100% is not possible, Q1 is equal to W is not possible. Why? Because there is loss. There is loss means the heat will transfer to surrounding. Okay, so always there is heat transfer from system to surrounding. The reverse is also possible. We can transfer heat from surrounding to system. For that we have to reverse this arrow. We have to do work done on the system. Means we have to move that piston our own. Okay, suppose this is our piston. Normally what happen? The combustion happen here and because of that combustion piston moves down. But suppose we have to transfer heat from surrounding to system, then what we have to do? We have to move this piston our own, or by using some motor, by using some external source, we have to move this piston. So these gases will get compressed, and as these gases will get compressed, there is some heat difference, pressure difference, and heat will transfer from surrounding to system. So generally we call it as refrigerator. In refrigerator what we do? We are using one compressor which will pump refrigerant and there is some pressure difference, expansion of gases will be there and it will transfer from surrounding to system in refrigerator. We will study this system or this application in detail in next lectures. So here we have to learn what is system and surrounding. You have to remember that we cannot use system alone. We have to use surrounding always with the system. Then only we can obtain work done. Otherwise Q1 is equal to W will be there and that will be violation of second law of thermodynamics. Okay, that we have to learn in next lectures. The 100% efficiency is not possible. So that is about system and surrounding. Also we have learned what is boundary. There is one another concept that we have to learn, that is universe. You might be know this, you have learned this in basic mechanical engineering. So what is universe? The universe is nothing but system plus surrounding. You know what is system? Suppose this is our system. Okay, this is our system and this is surrounding. System will transfer some heat to surrounding only. There is heat interaction between system to surrounding and surrounding to system always. Okay, sometimes we transfer mass also. Whatever mass will be there in system, that mass, that matter also we can transfer to surrounding. From surrounding some matter we can transfer to system. So we can transfer mass and heat. Now what is universe here? The system plus surrounding is nothing but our universe. So here we can show universe. So this is our universe. Okay. Now if you say I will transfer heat beyond this universe, that is impossible. We cannot transfer heat from this universe to anything, because there doesn't exist anything beyond this universe. We can transfer heat from system to surrounding, surrounding to system. What are the example of system? In this piston cylinder we are using gas here. Suppose we are using combustible gases, suppose we are using air. So this is nothing but system. What is surrounding? Generally we use atmosphere is our surrounding. Anything outside the system is surrounding. And when we measure properties, we measure properties of system only. Sometimes we measure properties of surrounding, but generally the properties of surrounding will not change because surrounding is large. Generally we use atmosphere, so its properties are P0, T0, V0, okay, which are dead state properties. It will not change, so we say it is dead state properties, because we know atmospheric pressure is around 1 atmosphere or 1.01325 bar. So that pressure will not change with small heat transfer. So it is always P0, T0, V0. System is small. As some small heat transfer will be there, system properties will change. So in thermodynamics we analyze the properties of system always. Okay, properties of system. Which properties? Pressure, temperature, volume, enthalpy, entropy is there. Okay, internal energy is there. So generally all these properties that we have to learn for system. So that is about system, surrounding and boundary. Also we have seen universe. In next lecture we will study what is system in detail. I will list out the type of system. Next lecture topic, type of system. There are generally 3 types. You are familiar with these types in basic mechanical engineering. Maybe you have studied all these system types, but here in detail we have to study. Open system is there, then closed the system is there. Okay, we say it is control volume also. Control volume, open system, then closed system and isolated system. So in next lecture we will study all these 3 systems. If you have any doubt, you can ask me that doubt in comment box. And also I have one request to you. Just subscribe this channel. I required 1000 subscribers to take live lecture on YouTube. So I need your help for that. So please subscribe the channel also. And also do one thing. In description box I have given quiz 1 that you have to solve. It has 10 questions. Okay, 1 mark each. So do solve this quiz, and if you have any doubt you can ask me. You can just put that questions in comment box. Thank you for attending my lecture. We will meet to lecture 2 in which we are studying this topic. Thank you so much.